Please take your seats. Yeah, we would like to start because the next talk is almost imminent after this one. Today we have again the pleasure for a very, very high recognition. It's the Max-Planck-Medal, and as said on Monday, this is the highest recognition the DPG gives to theoretical physics. And today we have the pleasure of Professor Andrzej Buras from Technical University of Munich. He got his medal already in 2020, yeah?
No, not
no,
really.
The prize is from 2020. So, and now we have the pleasure to hear his presentation. I read the Laudatio, this is in German, für seine herausragenden Beiträge zur angewandten Quantenfeldtheorie, fundamentaler Wechselwirkungen, insbesondere auf dem Gebiet der Flavour-Physik und der Quantenchromodynamik. So you gave crucial contributions to understand all these interactions, especially for the asymmetry of matter and antimatter, and for rare decays for bound states. And you have a very exciting title. It's news from the Flavour expedition to the Zeptouniverse. Please.
Nach den Erfahrungen von einigen Sessions möchte ich einen Schnelltest durchführen. Können Sie mich hören? Positiver Test. Dankeschön. I will now, of course, talk in English. I got the medal actually last June in Bad Honnef, and there I thanked it in German. So there are many foreigners here, so I will thank again for this medal. Thank you very much. It was really a great pleasure to get it, even if I had to wait because of Corona 3 years to give this talk. But there was some pleasure because some people were forgetting it. So I got congratulations from one person 3 times. So there was some advantage, and so on. So let me now with an overture. So it's an opening, and this is the first transparency I want to show. This is a bit out of date, but this is the one I wanted to show 3 years ago. I think it's still a very important one. And here is the second one, which I think, oh, I'm doing something wrong. Okay, I do it with this. This is the second one, which is equally important. And now one which is maybe not so important. And it took me 50 years. Can you imagine? 50 years to get this medal from my master. And you have to realize that in 50 years, there were dramatic changes in physics, in particular in particle physics, but not only in physics. And I got this master in Warsaw, but in 1971, I emigrated from Poland to Denmark to become a Dane 6 years later, but already on the first day almost, I was standing in front of this building on this side, looking at it. Niels Bohr was my hero in my high school years. And I was thinking, what will be my future in the West, in particular, my PhD in this building. And I could not predict, really I could not predict that 52 years later, namely today, I will be able to present this transparency. And I hope the computer will work, because yesterday somebody was making predictions for 2095, and I went beyond it, but it works. And this symbol here defines me for the rest of the talk, and I cannot really tell you what will be in 90 years from now, because this person probably was not born and for sure not decide to do physics. But I would like to realize that you realize from a moment that if this prediction is correct, this talk is the only talk by a Danish Max-Planck medalist in this century, and the only one you can witness in your life. And what does it mean for me? I have to do my best, and I will try. So I move immediately to something which I don't have to predict. And this is something which you have seen already many times. These are the particles which we know, and forces. And this thing with stars were in 1970, where I was doing my master. And I was really very privileged, really, to witness all these discoveries. Then there is Higgs, was discovered 2012. We know many things about the Higgs. We know also that it doesn't give masses to proton neutron, but there were many talks here, and indeed it looks like this is good. Now the question is, what next? And for a person of my age, I have to admit, the European strategy that you look in detail for Higgs doesn't interest me too much, because I'm really interested in very short distance scales beyond LHC. Maybe LHC will still find some particle, and the route to go there is simply through quantum fluctuation. And this is a strategy, indirect strategy, which is known actually for years. 100 years before my birthday, Neptune was discovered through anomaly in the orbit of the Uranus, and this guy who saw it, a French guy, was very lucky, because 1 year later, and maybe even the same year, it was confirmed, and I have to wait sometimes 30 years for what I predict. Now, this is the case of the black hole. Also, dark matter searches. By 1 hour ago, we heard dark matter doesn't exist. Very good news for me. I never worked on dark matter. And also Enrico Fermi, where he felt this W, and this he didn't know it was W's and Z's. People were starting discussing it much later, 1960, but eventually they were discovered. Now, what next? At least in this route to Zeptouniverse, I have colleagues in theory who claim there is nothing until the Planck scale, maybe right-handed neutrinos. Now, my view is completely different. I'm very optimistic. I love Flavour physics, and it's a very beautiful field. I will show you on transparency now, my vision. And even if you don't get anything from my talk, I hope you will remember this transparency until your last days. And this is coming here. And what you see here is a standard model, not so interesting. And then we are crossing at the moment this energy gap with the help of so-called standard model effective theory, which I'm spending 80% of my life, but it's too technical, so don't worry, I will not talk about it. And then we reach some crevices, the call experiments, and then eventually I hope we find this new physics summits. And compared to one talk on cosmology yesterday, where there were beautiful artistic views, this is a photo which made by my son, who is doing climate research. So this is like that. And now we will start our expedition. And this is the expedition from AtoUni to Zeptouniverse. There is a problem here. It is very difficult to imagine how small these distances are. And we know what is the problem. These are the minus signs. So there is a very simple solution. You remove the minus sign, and it will be much easier to see what is going on. And this is a so-called dual picture, which I suggested some time ago for talks like this. Maybe a bit similar to what string theories are doing, the dualities. And there are some string theories in the audience. Self-dual is 1 meter. So let us try this on the basis of nanoscience, because this is what you know. And this is nanometer in this dual. You see in this dual picture. And it's very interesting, because this is roughly the distance from the Earth to the Moon. And now you can imagine we are all as tall as this distance, and these guys are still collaborating 1 meter, 10 meter. Fantastic, fantastic. But I have to tell you, it's nothing, completely nothing compared to what we can do. Real peanuts, and you can see it already on the next example. And this is the case of TUM-IAS. Now, there is an object, Beta Ceti, and let us assume that during the first celebration, a signal has been sent to us. It didn't arrive yet, but what is fortunate, it will arrive for my 80th birthday. And you can see here the TUM-IAS. Now, this is already very interesting, but it's even more interesting is the next step. This is the goal of this expedition. And this is Zeptouniverse. And let us assume now a signal comes from there. And you can ask yourself, what was on the Earth when the signal was sent out? There was definitely no CMS collaboration, no Atlas collaboration, no LHCb collaboration, but there was another collaboration with rather very different goals, as you can see. This person here was probably a spokesman, and he didn't expect that I would cite him. This guy here is not very nice, as you can see, but this picture shows one point which you will see during my talk, that the Flavour expedition to the Zeptouniverse is a true mammoth project. I will prove it to you. But the thing is, this is exciting. If it was not, I wouldn't care so much about it. So now let us still look at this. It started with van Leeuwenhoek discovering bacteria, and there was following, probably beyond my 100th birthday, Femto-Universe, and so on and so on. LHC probably can reach 5 times 10 to minus 20 in my counting, uncertainty principle, and so on and so on. But you cannot go further. And I started actually already somewhere between Femto-Universe and TUM-IAS, and I want to mention one thing. At Fermilab, this was this paper which was mentioned in Laudatio. This was the lambda MS bar scheme, which we proposed, which is used at the moment by everybody. And this was, in fact, the first correct NLO matching of the full and effective theory in the standard model. Then, at Max-Planck-Institute, there was work on so-called large N number of colors, first with Gerard and Trückel, and then really an approach which was not mentioned in Laudatio, but I think it's very good because it's a bit controversial, on the application of ideas of Tooth-Witten large N, so-called dual QCD, but I will not have time to talk about it. Next, I moved to Technical University, and until then I had maybe 20 collaborators, but it changed completely. These are the topics that were mentioned, and I have very many diploma students, very many PhD students, many postdocs, and somebody had to pay for it. So I'm thanking everybody here. And for me, the most important at the moment is obviously this institute here, Technical University Institute for Advanced Study, because they promised me to keep me until I turn 100. What will happen afterwards, I don't know. And so I'm thanking really very much. And I had very many collaborators. And what was really nice, I have to tell you, many ladies, 21. And I have to tell you, male physicists don't like it. Women are much better organized. Now, this was not like collaboration, you know, Atlas and so on, 2 papers. And some of them you will see. It was very interesting. But now I would like to thank 3 gentlemen, and maybe not only 3, whom I never met. I had only contact with them online, but they were really instrumental for my research. And these are the 3 ones. And I'm listening all the time. I cannot work, which irritates my wife because I don't want to. So I play. And then one message to younger people, if you have some problems, just listen to this triple concerto and you will solve everything. This is what happens always with me. I play triple concerto. And in this moment, I hope you expect what will come. What comes now is a symphony, the shortest one maybe until now. And what happens is that the most important will be the second movement, and maybe the third, and the message to chair lady, finale, only 2 minutes. So we will see how it goes. And so let us move to the first movement. And I will be very short because there are excellent talks already on that. And we show only here only one transparency. And this is, I'm talking about flavor. And the only flavor which we have in the standard model is this vertex which you have, which is not simple. It is a matrix, a unitary matrix, and it has a very peculiar shape. It's almost diagonal. It has a phase. One, this is this gamma here. This is this gamma here which you have. And this is not a small one, 65 degrees. The other one is related. There is only one phase. And if these coefficients in front of these phases were not so small, maybe we could explain our existence, but we cannot, because there are, of course, other effects and so on, which we have. And we know that this model works very well. But there are, of course, questions. Could be particles, new particles, forces, the original mass, actually neutrino masses, which I didn't mention, but you can see they are not in the standard model of the hierarchies. Y is proton, neutron heavier than proton, and so on and so on. And none of these questions can be answered in the standard model. And I don't know whether LHC will produce still some particles. So we have to go a different route. And now I want to explain the basis of this route. So the main players at the moment are bound states of quarks, anti-quarks. They have names here. Okay, particle physicists, anyway, they are known, the mesons. And they are not very heavy. So they are producing billions at LHC. They are short-lived. They decay in lighter particles. Experimentalists measure probabilities for this to happen to a given state, what we call branching ratios, and we calculate it and we compare. And now let me show you only one Feynman diagram, not a very simple one. So what we have here, we have this bound state, the B+, and there is a connection, there is a transition with the help of the W to leptons. A very simple one, and I can calculate the probability where the coupling square propagator is one of a W squared. There are some parameters I can predict it. But let's assume that there is a particle which LHC cannot see. Heavy, not heavy scalar here, but some heavy charged particle, sometimes called W prime, and it can also do it, but you cannot see it. It comes 10 to minus 23 seconds or something like that, but it's enough to change this probability. And so I calculated the change. Sometimes it happens there is no interference with the first contribution, so I know it will be increased. But very often, there is interference. And if B is negative, I will get simply a different, smaller probability, smaller branching. But we know already for all this technology for many years that this is the way really to feel something. And here is one example. The other one was 10 to minus 4. This is 10 to minus 9. I calculated with Gerhard Buchala, who you will see still in 92. We waited 30 years to see whether it's confirmed. And unfortunately, it works pretty well. But I probably will not talk. So it shows you have to stay healthy if you know, to see it. And this is, you try to get something what it is blob. But even if there was deviation here, there is no way to find out what it is. You will have hundreds of theories who will tell you different things. So the only way to do it, you have to make many precision measurements of many observables and very precise theory. And then, and this is more my strategy, study pattern of violation. Before you go start playing with the global fits, you look at given models, start correlations, and so on and so on. So, but now let me go still to one point. And this is something I had very many collaborators, mainly my PhD students, but I would like to mention here on this QCD calculation, in particular Peter Weiss and Yamin, with whom I started. And then these four gentlemen, one is sitting in the lecture room, who really contributed very much. And I should still mention too, I almost have forgotten, Christoph Bobet and Jörg Urban, they studied here, and then they came to me, so I was very lucky. Now, the second point, my group, I claim, and I'm sure I'm right, is the only one on this planet, at least on this planet, which calculated 20 or even more new physics models. These models really have been worked out, Feynman diagrams, rules, and so on and so on. They are waiting for experiments, and then we will see maybe some are ruled out, some not. And for this to make, you need a full army. And this is my Italian army. I worked with many Italian physicists, many in my group, very well known, like Fulvio De Faccio, Isidori Silvestrini, and a few others. Then I had first group of non-Italian collaborators, and I want to mention here two ladies, and this is Monica Blanke and Jennifer Gierbach-Neu, who is my granddaughter in physics. Monica is my daughter in physics, and these are the ones with whom I written even separate most papers, 20 papers each, and the only one who can compete male is this Jean-Marc Gérard. And then I had non-Italian collaborators. And the thing is, we developed very many techniques which are too technical to be presented here. And I want to show you only one example. And this is an example that you simply look at in a given model and look at the probability will be increased and so on. And then you work full time and you study all these properties at the case. And then you construct something like that. There could be correlation between plus and minus. This is the only thing what I wanted to say. And this is mainly what I could show you in Bonn. But then Corona came. I disappeared in the home office, and I got new collaborators. And so now come the news, and the news come directly from my home office here. And the news start not so good for some collaborations. And this is the following. I made a point 6 months ago that if you calculate a branching ratio, two things are very already under control, perturbative QCD, non-perturbative QCD, you have various approaches, but to make prediction, you need Kobayashi-Maskawa factors. And those are done in some, in some global fits, but my point is the following. If one observable there is infected, the modern language, by new physics, the Kobayashi-Maskawa will be infected, and the branching ratio will not be really the one which you otherwise you would get. And so the other problem is the tension between the VUB and the VCB, which I will mention is like Hubble constant. Maybe the third point is not so exciting. So what is the solution? The solution is suggested by me already 20 years ago for B physics and developed with Elena Venturini 1 year ago. You just try to hide, because they should not be infected, Kobayashi-Maskawa parameters by taking the ratios of a given branching ratio to given difference. And you can eliminate completely Kobayashi-Maskawa for B physics. The one variable for K physics is only beta. And then what you do after what I said that, I don't want to play with these tensions and so on, you do a sub-fit. You take only these quantities, which maybe I know to others. There are some quantities which I can measure. They are very well measured. They are very well calculated. And I set them to experimental values. And this is something which is done in a global fit. And in this manner, I get a very precise prediction, most precise to date, because theory and experiment for these observables are very good. And then I have to do a rapid test. I have to prove there is no infection. And the rapid test of infection for these observables is with so-called VCB versus gamma plots. I will show it to them. And then the test will be negative. So I can get Kobayashi-Maskawa. Until now, I didn't need them. And now you can see what are the advantages. These observables seem to be very surprisingly free of infection. The remaining observables outside this delta, what Galapagos was not infected so much, have some infection. This is what we hope. And then I can simply estimate and calculate the pulse, and all this can be avoided. Now, you can imagine that not everybody is happy with this. And I went to Rome, UT Fides, in September after this talk. And I expected something like this. But it didn't happen. The lion, this is already 6 months, didn't jump on me, but I'm waiting. And let me now very briefly tell you only this one of UB is not so serious, this issue of VCB. And you would say, oh, okay, this is not so bad, this is 10%, but this is a disaster. This is a disaster for people like me, who calculated very precisely all these QCD corrections, and lattice also improved very much. And if you start varying from 39 to 42 in these units, you can see this is really very bad. So I want to show you one ratio. And this is the one where, in fact, I don't even need gamma. LHCb didn't really get... and this is something, one of the examples. I set this to be equal to the data, and I get very accurate prediction with Elena Venturini. And they are by factor 2.4 and 4 improved over what we did in 2015 with other group. And this is actually very interesting if in this parameter epsilon k, because this is one of the observations, there is no new physics, because as pointed out many years ago by my brilliant student Monika Blanke, in this particular case, the action in the correlation of the Studi case, which now are studied at Koto and NA62, will only go on these two branches. And this one is much more interesting because on this branch I have also effects of so-called direct CP violation. On the other one, there is not much happening, and this is what we investigated recently with a Z prime. And what happens is, this is this branch, that if you measure one day much more precisely this ratio, which is unit in the standard model, then this is the branch, and you will have fantastic correlation with other observables, which I cannot enter here. And this is the test. You can see it is negative. One can do a bit better. Two positive tests with different matrix elements. And what is really amazing, because infection is very popular these days, that these three plots made the cover of the European Physical Journal C, the first one. But it's even more interesting. I was invited to a medical conference to report on them. These are the matrix, the values, and I get the values, we get values a bit higher than what, for instance, Gambino is getting in the inclusive, but much higher than exclusive. And I think I have to, I'm sorry, I'm a bit over time, but maybe still a few minutes. I want to tell you something, anomalies. There are many anomalies, but in fact, there is here one disappeared, as you know, so let's not talk about it. I will talk about only this one. And the others, if you ask me, we have time. So these are, as we had this morning, these are mainly the particles may be responsible for them. Dinosaurs, maybe the leptoquarks are, I think they are getting harder. The others. And from my strategy, and this is interesting, I really want to tell you, because it's much more precise, it's free, I get much bigger anomalies in a single, and this is not something I made mistake. I asked some people to test, really 5 sigma. And so this is really 5 sigma. And for a moment, it is like Eigentor. Because you have to realize, I said there is no new physics in delta MS. I predicted this 5 sigma, now I have to explain it. And if I, as you can see, if I take here, want to explain, because this is a diagram for this anomaly, and then I immediately have a contribution to delta MS. And then, however, you think about it, especially under the shower one day, that there were problems also in the 1960s with the scale longitude muons, and what these people did at the time, they simply had 3 quarks. They added the 4th quark and solved the problem. So my idea is, this is a very recent one, you take 2 Z primes. And you can arrange really the couplings, that they collaborate, they remove new physics from the mixing, and they collaborate to explain the anomalies. And I think this is an interesting framework, although I'm, of course, biased by this, because it somewhat separates the determination of CKM parameters, and these are the vertices of the prime. And they collaborated, but I have to tell you the other solution. The only thing they have fine-tuning, if you can draw a few other diagrams, the prime with different couplings, you can solve it. But the point is, for this to work, you need Z prime. And so I have now the message. Please find Z prime as soon as possible, because I'm not the youngest. Or at least one of them. Because if I find one of them, then maybe through this correlation I can get the other one. So I'm finished now, 1 minute, 2 minutes. So I hope I convinced you. There will be really a lot of fun, especially this decade, in going there. And exciting time. I should stress there will be many experiments which really will tell us something. And there are various other G-2 epsilon prime over epsilon, CP violation, also delta equal half rule, which is with us already since '54. And it's not fully explained. Maybe there is new physics. I worked a lot on it, but I will not tell you now anything, no time. I hope we meet these 2 guys on the way. And there is a commercial coming in the final part. This is the book I have written. This is a mammoth project for 7 years, very exciting one. And now it's the following, that if we meet, let's say, in 10 years, maybe again in Dresden, then there is one obvious prediction: we will be all 10 years older. But I'm sure in my case, I will be still very optimistic that we are coming to the Zeptouniverse and really maybe reaching it. But I have to stress, we have to be prepared that this expedition will last a bit longer. Thank you very much.